Occam's razor is a powerful principle that seems so reasonable and compelling that when it is broached in an argument against a point, that point can immediately lose its footing. However, the principle, like all principles, can be misapplied. This video will quickly develop a thought experiment designed to be analogous to the situations when the principle is misapplied. We want to construct a theory of X, where X has a finite number of elemental parts and a finite number of laws. For this discussion, let's assume the laws and the elementals are independent of each other. The laws govern the behavior of the elementals. Now, we will focus exclusively on the laws. Suppose we have a collection of elementals interacting, and our goal is to identify the number of laws, L, responsible for the observed outcome. We assume that the same set of laws operates on all elementals in the system, and L lies between 0 and L. Let's introduce a statistical perspective here. Suppose the expected value of L is m, with a finite mean and variance. Although we may not know the specific distribution for L, we can still estimate that L falls within the range m 4.47s is less than or equal to L is less than or equal to m plus 4.47s, for a 95% confidence level, where s is the standard deviation. For example, if m equals 5 and s equals square root 0.2, we find that, approximately, 3 is less than or equal to L is less than or equal to 7. Thus, the possible number of laws could range from 3 to 7. Here we have assumed no information about the laws of X and so simply applied Chebyshev's estimate for the mean. If one were to carry out this project, in fact, one would study the distribution of the number of laws in similar theories related to X. Chebyshev's is the worst reasonable estimation of L, but it at least always permits an estimate of L. The exact value of L cannot be confidently placed closer to 3 or to 7, and thus the best strategy may be to select L equals m, in this case, 5 laws. This statistical reasoning suggests that selecting 5 laws on average would outperform choosing a smaller number, like 1, 2, 3, or 4 in terms of likelihood, because there is no reason to choose the lower estimates statistically. In this scenario, Occam's razor, which pushes us toward fewer laws, might lead us to underestimate the number of necessary laws if we always favor the simplest solution. This means that strictly adhering to Occam's razor could result in missing plausible solutions that involve more than the minimal number of laws. Without knowing the exact distribution, the probability that the theory involves fewer than 5 laws is 47.5%, and the probability that it involves more than 5 laws is also 47.5%. This implies that Occam's razor is not always the optimal approach in this context because it may steer us away from the correct number of laws by overemphasizing simplicity. So, what is the real point of this argument? Occam's razor is usually applied once 2 or more viable solutions or theories are available to explain a subject. Occam's razor does not usually help in the determination of the number of laws a proposed theory must have before the fact. The point is that in many arguments about philosophical and scientific topics these days, an appeal to Occam's razor is made well before a potential solution to the question has been arrived at. This is akin to selecting the number of laws as in the demonstration. And this is our focus. That said, Occam's razor still applies in cases where 2 theories fit the same set of facts and produce equally successful predictions. In such cases, the simpler theory is typically preferred unless the more complex theory provides additional advantages, such as greater intuitive appeal or explanatory depth. In these end-stage theories, Occam's razor guides us toward parsimony. It can be argued that simplifying a solution as one goes along may be a better strategy, but in the early stages of theory development, we should be more flexible. In the beginning, our focus should be on accounting for the data and explaining the observed results, rather than simplifying prematurely. We are in reality looking at the sample space as in our thought experiment and making informed guesses at the number of laws or elements of a solution necessary to solve the problem. When we engage in discussions and formal arguments, we are looking to add to our understanding and analysis of the problem. But when Occam's razor is thrown in, it is as though we have been asked not to speak on the issue. But we are taught to defer to Occam's razor. Who can stand against it? Well, the point is that there is a kind of thing the principle applies to, and there is a kind of thing it does not apply to. The point is that it does not generally apply when there are not 2 developed theories having the same footing. At this point, it's important to note that Occam's razor is not well suited for theories involving normative laws, which often involve self-reference and lack the homogeneity found in empirical laws. Normative laws don't behave like typical theoretical components, which raises concerns when applying Occam's razor to these areas. This suggests that Occam's razor may not be universally applicable, and a more technical evaluation of its appropriateness is necessary in each specific case. An example of Occam's razor misapplied to a normative law is love your enemies. Occam's razor might reduce this to the strict verbal commandment, when the application of this command does not imply that one give up the struggle and embrace all your enemy or adversary does or stands for. In conclusion, appeals to Occam's razor may be inappropriate during early theory construction. And during discussions of provisional theories, when ideas are being showcased, appeals to Occam's razor may be closer to a logical fallacy than a legitimate arguing point, for it implies that the two or more theories under discussion are on precisely the same footing. And it implies that the theories are end-stage theories that can support the weight of such rigid standards.